This talk is about polyhedra. So what are they? In particular, what are the Platonic and Archimedean solids? And what other polyhedra are there? And what is Euler's polyhedron formula, and can it be generalized? A polyhedron, meaning many faces, is a three-dimensional solid with polygons as its faces. Any two faces meet along an edge, and three or more faces meet at each corner or vertex. Here are three examples: a cube with its 6 square faces, 8 vertices, and 12 edges; a square pyramid with its 5 faces, 4 triangular and 1 square, and with 5 vertices and 5 edges; and on the right, a truncated icosahedron with 32 faces, 12 pentagonal and 20 hexagonal, and with 60 vertices and 90 edges. The cube is an example of a regular polyhedron, where the faces are all regular polygons of the same type, and with the same pattern of faces appearing around each vertex. In total, there are 5 regular polyhedra. 3 of them have triangular faces: the tetrahedron, meaning 4 faces, the octahedron, 8 faces, and the icosahedron with 20 faces. There are also the cube or hexahedron with 6 square faces, and the dodecahedron with 12 pentagonal faces. These polyhedra are often called Platonic solids because they were described by the Greek philosopher Plato in his dialogue Timaeus. Here you can see Plato on the left carrying the Timaeus, with Aristotle on the right, from Raphael's celebrated fresco, The School of Athens. In this dialogue, he associated the 5 solids with the 4 Greek elements of fire, represented by the tetrahedron, earth, the cube, air, the octahedron, and water, the icosahedron. The remaining solid, the dodecahedron, he associated with the universe. These polyhedra were also known to various ancient civilizations. Here are some polyhedral stone balls from Scotland, dating from Neolithic times, and below is a Roman dodecahedron. It's not known exactly what their purpose was. These polyhedra were also investigated by the German astronomer Johannes Kepler. In his time, only 6 planets were known, and in an attempt to propose a model for the solar system, he described how their various orbits might fit snugly around the 5 Platonic solids, as illustrated here, with the cube outermost, followed in turn by the tetrahedron, dodecahedron, icosahedron, and octahedron. Although his model was not widely accepted, especially when new planets were discovered, his idea of a model for the universe proved to be of great significance. Polyhedra also arise in nature. They appear as crystals of various chemicals, such as the cubic, octahedral, and dodecahedral crystals of iron pyrites. They appear too as radiolaria, which are the skeletons of certain marine sea mammals. This one has the form of an icosahedron. Returning now to the Greeks, we find the 13 semi-regular polyhedra, where the faces are still regular polygons, but they're not all of the same type. For example, the one at the top right is made from squares and equilateral triangles, while the one in the centre is the truncated icosahedron we met earlier, with its pentagonal and hexagonal faces. These solids are sometimes named after Archimedes, who supposedly described them in a work that's now lost. These polyhedra were also investigated by Kepler. Here are his drawings of them. He also gave them delightful names. For example, number 4 is the truncated icosahedron, so named because we can get it by cutting the corners off an icosahedron, while he named the large one, number 7, the great rhombicosidodecahedron. Another person interested in these Archimedean solids was Leonardo da Vinci, who illustrated some of them for a 16th century book on divine proportion. Here are his drawings of an icosidodecahedron on the left and a small rhombicube octahedron on the right. What other polyhedra are there? Here are a few more. On the left are 2 images of a stellar octangula, formed by squeezing together 2 tetrahedra. Above, in the middle, a dodecahedron and an icosahedron have been combined, while below it is the so-called great dodecahedron. And on the right is the great stellated dodecahedron, and below it is an attractive polyhedron formed by linking together 5 tetrahedra. We come at last to Euler's polyhedron formula, first presented in 1750 by the Swiss mathematician Leonhard Euler. It states that if a polyhedron has V vertices, E edges and F faces, then V minus E plus F is equal to 2, or in the form that Euler presented it, faces plus vertices equals edges plus 2. As examples, a cube has 8 vertices, 12 edges and 6 faces, and 8 minus 12 plus 6 equals 2. While a dodecahedron has 20 vertices, 30 edges and 12 faces, and 20 minus 30 plus 12 equals 2. And the result applies also to the semi-regular polyhedra. For example, the great rhombicosidodecahedron has 120 vertices, 180 edges and 62 faces, and 120 minus 180 plus 62 equals 2. Here's the formula's first appearance, in a letter from 1750 that Euler wrote from Berlin to his friend and former colleague Christian Goldbach, known for Goldbach's conjecture in number theory. It appears in paragraph 6, in the form H plus S equals A plus 2, where H is the number of faces, hedrae, S is the number of solid angles, or vertices, and A is the number of edges, acies, a term that Euler himself introduced. Below he applied his result to a prism, where H equals 5, S equals 6, A equals 9, and 5 plus 6 equals 9 plus 2. And he remarked, "These general results in solid geometry have not previously been noticed by anyone, so far as I am aware." Euler's polyhedron formula has sometimes been attributed to the French mathematician and philosopher René Descartes, who obtained a result from which it can be deduced. But Descartes actually never made the connection. Let's now look at polyhedra whose faces are all pentagons or hexagons. An example is the truncated icosahedron in the centre, which is probably more familiar to us in the form of the soccer ball on the right. Here V is 60, E is 90, F is 32, and V minus E plus F equals 60 minus 90 plus 32 equals 2. Such polyhedra were of particular interest to the American architect Buckminster Fuller when designing his massive geodesic domes like the one pictured below. And they've also arisen in a chemical context as fullerenes or buckyballs, molecules that are named after him, such as the one shown on the right. Such polyhedra may have many vertices, but if exactly 3 edges or 3 faces meet at each one, as in a football or any buckyball, then however many hexagons there must be exactly 12 pentagons. For if there are P pentagons and H hexagons, then F, the total number of faces, is P plus H. And if we count up the edges around all the faces, we get 5p for the pentagons plus 6h for the hexagons. And this equals twice e, with the 2 arising because each edge meets 2 faces and is therefore counted twice. And on counting up the 3 edges at each vertex, we similarly get 3 times v equals 2 times e, because each edge meets 2 vertices. And this again is 5p plus 6h. If we now substitute these values into Euler's formula v minus e plus f equals 2, we get the equation shown here. Here the h's all cancel, and we're left, after some algebra, with p equals 12. That is, there are exactly 12 pentagons. Something you might like to bear in mind the next time you see a geodesic dome or watch a game of soccer. Up to now, our polyhedra can be drawn on a sphere, such as our soccer ball example. But how about polyhedra drawn on other surfaces? Such a surface is the torus, which is the surface of a ring donut, a bagel, or a rubber tire. Is there a version of Euler's polyhedron formula for these surfaces? Back in 1813, a Swiss mathematician called L'Huillier was investigating polyhedra with a tunnel bored through them, that is, polyhedra drawn on a torus. And he proved that v minus e plus f is no longer equal to 2, but is now 0. For example, the polyhedron on the left has 16 vertices, 32 edges, and 16 faces, and 16 minus 32 plus 16 equals 0. And moreover, whenever we create another tunnel, the value of v minus e plus f goes down by a further 2. And another way of saying this is that if our surface is a donut with g holes in it, then Euler's formula becomes v minus e plus f equals 2 minus 2g. So for example, for any polyhedron drawn on the 2-holed surface on the right, where g equals 2, we have v minus e plus f equals 2 minus 4, which is minus 2. So Euler's polyhedron formula can be generalized to these other surfaces too. And with that result, I thank you for listening.